All right, guys. So today we start Unit 3, new quarter, kind of a fresh start that we have here. And we're going to start out by talking about functions. Remember you've dealt with functions for a long time. A function is basically an equation, but instead of something like 3 equals 2 plus 1, a function looks like f of x equals 2x plus 1, where f of x is the output. And usually when we're talking about a function that lives on a graph, that's our y value. But for whatever value x we plug in to the equation, we're going to get an output that represents y on our graph. So we've got an input x and output y. And we're going to get into that in a lot more detail as the next couple of weeks go on. But the first thing that we want to talk about when we're dealing with functions is interval notation. And this is something that we'll see a little bit later in the video come into play, but it's something that you need to understand how it works. And I know that these little symbols right here are going to cause some of you some grief. You've been dealing with them for a long time, the less than, greater than signs. But a lot of you are still struggling with what represents what. So interval notation looks like this. 2 is less than or equal to x, which is less than 5. So this is an inequality, but it's a combination of two different inequalities. It's a combination of 2 being less than or equal to x and x being less than 5. Okay, so the way this works is 2 represents the left endpoint of the interval. And that includes 2 because of this equal sign underneath the less than. And the 5 represents the right endpoint of the interval, but it does not include 5 because there's no equal sign underneath the less than. So what this looks like, normally when you have something like x is less than 5, on a number line, that means if this is 0 and this is 5, you used to put a circle at 5 because x can't be 5, and then you would draw an arrow to the left because x is all of the numbers that are less than 5. Now that's changed a little bit. Not only is x less than 5, but x is also greater than or equal to 2. So what this looks like on a number line, if I still have my number line here and here's 0, I'm going to mark my critical points 2 and 5. And what that means is x is in between these two numbers. So I still have an open circle at 5, but at 2, I have a closed circle because x can actually be 2. And so x is all of these numbers in between 2 and 5. That's what this represents. X is something in between 2 and 5, and 2 is one of the options. Okay, so in interval notation, we use brackets to represent endpoints that are included, like this one. We use brackets when there's a less than or equal to part, and we use parentheses when there's not the equal to part. So like this one right here. The 5 does not have an equal to underneath it, so we would use parentheses. And the way that you write it in interval notation is x is going to be in the middle of 2 and 5. And the way we write that is I put a bracket to represent the left-hand side right here, and that includes the number 2. And then I put a comma, and I can go all the way up to the number 5, but I do not include 5, so I use a parenthesis on the right-hand side. So what this tells me is that my number is somewhere in between 2 and 5. I know it kind of looks like a point on a graph, but this is called interval notation, and that bracket makes the big difference there, okay? But this just tells me that I'm living somewhere between 2 and 5. So we're going to try it on a couple of these. 1 is less than or equal to x, which is less than or equal to 6. So that means x is in between 1 and 6. So those are the numbers I'm going to use. and I have a less than or equal to on the left, and I have a greater than or equal to on the right. So I'm going to use a bracket for both of those. Okay. In the second example, x is in between -5 and 6. So I'm in between -5 and 6. But this time I don't include -5, so I put a parenthesis, but I do include 6, so I put a bracket on the right-hand side. Okay. Sometimes you'll get one like this: x is greater than -6. And there's a little note down here at the bottom that says if you only have one value, one of your endpoints is going to be infinity or -infinity. So if x is greater than -6, that means x is going to go from -6 up to infinity. There's no endpoint at the top. And we always use a parenthesis with infinity. And then on the left-hand side, because this doesn't have an equal sign, I'm going to also use a parenthesis. Okay. On this one, x is less than or equal to 13. So x is smaller than 13, which means it's going to go from -infinity up to 13. And because it's an infinity, I always use a parenthesis. And this is an equal sign with the 13, so I'm going to use a bracket on that side. So basically, this is just a notation that we use when we're talking about functions to describe where our numbers are going to be. In between 2 and 5, including 2, in between 1 and 6, including 1 and 6, and so on. So what I'd like you to do, pause the video and open up homework number 11. And I want you to try numbers 1 and number 2 on your own. And when you're done trying those, go ahead and start the video back up, and we'll move on. Okay, moving on. Absolute value functions. We're going to be talking about a lot of different functions over the next couple of weeks. And the first one is an absolute value function. And just so you can see what it looks like, f of x equals the absolute value of x. This is what we call the parent function, meaning it's the plain parent simple function. Nothing's being changed about it. This is just the original called parent function. And what that looks like, to give you an idea, is if I go to y equals, we actually have an absolute value button. If I click on math and I go over to number, the first option says ABS, and that stands for absolute value. And then when I click on that, you'll notice it puts the absolute value bars. And I just want to put x in the middle. And then when I hit graph, this is what my parent function looks like. This is what the absolute value function will always look like, a V. It may be upside down, but it's always going to be in the shape of a V. Now, one of the things that it's going to ask you to do on the homework and the ACT and the test is to use a table to graph what the function looks like. And this is a good review because what it's asking you to do, it says that f of x equals the absolute value of x. And it's asking you to plug in different values of x. So this is basically asking me if x is -3, and I plug that in right here, what is f of x? So if I plug -3 in right here, the absolute value of -3 is equal to 3. If you don't remember what absolute value means, remember that's how far away that number is from 0. So it doesn't matter what's on the inside, distance is always positive. So it's not the opposite of -3, it's the positive version of what's ever on the inside. So -3, the absolute value of -3 is +3. So when I plug in -3, I get out a 3. When I plug in -2, my output is +2. When I plug in a -1, my output is +1. When I plug in a 0, the absolute value of 0 is just 0. And then when I get to the other side of my x's into the positives, the absolute value of 1 is 1 because 1 is 1 away from 0. The absolute value of 2 is 2. The absolute value of 3 is 3. So you just, to make the table, you plug the values in for x and write down the outputs. And what this gives you are your points on the graph. So what this translates into is the point -3, 3. So if this is my graph right here, we'll call this, we'll make that our 0. And I'll try and draw a straight line today. We'll pretend that's straight. So -3, 3, I go over 1, 2, 3, and I go up 3. There's 1 point. -2, 2, that's what this one represents. So I go over 1, 2, up 2. -1, 1, that's what that represents. So -1, 1, 0, 0 is right here. And then I go the other direction. 1, 1 is here, 2, 2, and 3, 3. So there's your absolute value graph that I showed you on the calculator, but that's what it looks like when you draw it yourself. Okay, and that's something that you're going to need to be able to do. The functions won't always be as simple as the parent function. In fact, what we'll start doing and what you'll see on the homework is we change the function. So f of x, instead of just equaling the absolute value of x, we're going to add 3 to it. And what that does is it shifts my graph somehow. So if I start plugging in my x values, if I plug in -3 to this, I get the absolute value of -3 plus 3. This is 3 plus 3, so that becomes 6. Then I plug in -2. The absolute value of -2 plus 3 becomes 2 plus 3, so that becomes 5. When I plug in -1, I get a positive 1 plus 3, which is 4. And when I plug in a 0, 0 plus 3 is 3. Then I plug in a 1, 1 plus 3 is 4. Plug in a 2, 2 plus 3 is 5. Plug in a 3, 3 plus 3 is 6. So my graph has changed a little bit. We'll still go with, we'll make 0 down here still. And again, we'll try and get somewhat of a straight line here as I whiff that one pretty hard. Okay, so -3, 6 is our first point on our graph. So I go over 1, 2, 3, and I go up 1, 2, 3, 4, 5, 6. I go over -2, and I go up 5. I go over 1, and I go up 4. Then I go over 0, up 3, and then it's going to look the same on the other side. So if you notice what that did to my graph, having that +3 on the outside shifted my graph. It's the same picture, it's just shifted up 1, 2, 3 spots. And that's what this +3 does, is it's going to shift up 3. Now, what if the adding or subtracting is happening on the inside of the absolute value? It affects it a little bit differently. If I plug in a -3 for my x, then I get -3 minus 1. And we have to be really careful. The absolute value part of this comes very last. I can't just change these to positives right now. I have to do all the math on the inside first and then change my final number. So -3 minus 1, that becomes the absolute value of -4, which happens to be 4. So then I plug in a -2. So the absolute value of -2 minus 1 becomes the absolute value of -3, which becomes +3. And then when I plug in a -1, I get absolute value -1 minus 1, which is the absolute value of -2, which becomes 2. Plug in a 0, 0 minus 1 is -1. Absolute value of -1 is +1. And if you haven't noticed the pattern yet, on this side, when I plug in a 1, we've got to be careful because a lot of you are going to start saying, oh, that means this must be 2, 3, and 4. But when I plug in a 1, I get the absolute value of 1 minus 1, which is the absolute value of 0, which is 0. And then I plug in a 2. So absolute value of 2 minus 1 is absolute value of 1, which equals +1. And now I start repeating the other side of the graph. 3 minus 1 is 2. Absolute value of 2 is +2. So this time, if this is my graph here, we'll call this point our 0, 0. This time, negative 3, 4. So negative 1, 2, 3 goes up 1, 2, 3, 4. Negative 2, 1, 2, 3. Negative 1, up 2. 0, 1. And then 1, 0. And then 2, 1. So over 2, up 1. Over 3, up 2. So this time, instead of my graph shifting up and down, that minus 1 on the inside shifted my graph to the right 1 space. So this shifted me right 1 space, okay? Those are called translations, and we're going to get a little bit more in depth there. But what I want you to do is pause the video, and I want you to try numbers 3 and 4. It's going to have you fill in the tables and then graph the picture when you're done of what the graph should look like. So try number 3 and 4 on homework 11, and then hit play again. All right, so moving on. As you're noticing, depending on what I add or subtract or multiply by, that's going to change my original parent function. And remember, the parent function is just our original absolute value of x. That's called a parent function. And here's just kind of a breakdown of how it shifts, okay? If I have a number on the outside after the absolute value, if I add or subtract, that's going to shift my graph up. If I add, it's going to shift my graph down if I subtract a number, okay? If I add or subtract on the inside, we have to be a little bit careful, because if I subtract a number, that actually shifts me to the right. And if I add a number, that's going to shift me to the left. And then there's something that's called vertical stretch and compression. And we haven't seen this yet, but we'll see it in the next example. If there's something in front of the absolute value being multiplied, if it's a number that's bigger than 1, then it actually stretches my picture. So in other words, if I had something like 3 absolute value of x, instead of being my normal graph, it's going to be a lot skinnier. We call that a stretch because it stretches it taller. And if I have a number in front that's a fraction, like 1/4, if I had something like 1/4 absolute value x, we call that a compression, because that actually takes our graph and makes it short and squatty. Okay, it compresses it, it makes it shorter and wider, shorter and fatter. And then if I put a negative sign in front of the absolute value, that's just going to turn my picture upside down. Okay, if there's a negative on the inside, it reflects it across the y-axis, which we're not going to really see in this one, so we won't worry too much about that. But if it's on the outside, if there's a negative in front, then it's going to flip my picture upside down. So what's kind of cool about this is, if you know these things, you know what the graph is going to do without having to look at the picture. Okay, you can look at the function, you can look at the numbers, and you can tell what the graph is going to do. So for example, what is the graph of the function y equals absolute value x minus 2 plus 1? What is that going to do when I graph it? So one of my options is to plug a whole bunch of numbers in for x and then draw the picture, or I can look at what's happening in the math. So first of all, I have a minus 2 on the inside of my absolute value. So that means it's going to shift to the right 2 places. And I have a plus 1 on the outside of the absolute value, which means it's going to shift up 1. So instead of starting at 0, 0, like I normally would, normally I'd start right here at 0, 0, but I'm not going to. I'm going to shift over 2 and up 1. So I've got to go over 2 and up 1. So this is going to be my vertice, or my vertex, instead of 0, 0. And then from there, it just goes up 1, over 1 in each direction. So rather than having to graph that or use the table or use my calculator, I can just look at the numbers and tell what the graph is going to do. Okay. In this case, I have a 3 in front of the absolute value. And what that means is it's going to stretch me vertically, which means it's going to make me taller and skinnier. So my normal graph, the way that would normally work, notice I'm not shifting anywhere, so I still start at 0. But normally I would go over 1 and up 1. This is what my normal graph would look like. Okay, that's normally what I would do. But I'm being stretched vertically by 3, which means when I go over 1, I go up 3 instead of only up 1. So I go over 1, up 3. So this way I'm going to go over 1, up 3. I'm going to go over 1, up 3 again. So my graph is going to look taller and skinnier like this. Okay, I can still plug in numbers and try and do it that way. But I don't have to, because I can just look at the math. I can look at the function and tell what my graph is going to do. In this case, I have a fraction in front of the absolute value, and I have a negative. So the first thing that means is that it's going to flip my graph upside down. So I know that my graph is actually going to go down instead of up. So I'm going to start up here. And what this 3, 4 means is that instead of going over 1 and down 1, since I'm negative, what this means is I'm actually going to go over 4. So 1, 2, 3, 4. And I'm going to go down 3. 1, 2, 3. And then I'm going to go over 4. And I'm going to go down 3. So my graph is going to look shorter and wider than it normally would. Okay, not as dramatically, but normally this graph, just to give you an idea, if this was just negative x instead of the 3/4, I would go over 1, down 1, over 1, down 1, over 1, down 1, this way in both directions. And it takes a minute before you start to see the difference in what those two graphs look like. But they are different. This one is shorter and wider than the original parent graph. So what I'd like you to do is try number 5 and 6 on your homework, on homework 11. Pause the video, give those a try. What it's going to ask you to do is explain what is happening to your picture. Okay, so in this case, I would say that it's being translated to the right 2 and up 1. In this case, it's being stretched by a factor of 3. And in this one, it's being compressed by a factor of 3/4. And it's being reflected over the x because of that negative right there. So give 5 and 6 a try. When you're done, restart the video and we'll finish off the rest of this lesson. Okay, back with you. One of the most powerful things about this idea is about knowing what the numbers are going to do to the graph is you can find a lot of things easier, okay? For example, we can figure out if the graph is going to be short and wide or if it's going to be stretched tall and how much it's stretched by. We can also figure out where the vertex is without having to graph it and look at the picture. And we can also find the axis of symmetry based on this idea of knowing how the numbers affect the function. So normally we have y equals absolute value of x. But all of these different things can happen to x. You can have an a being multiplied out in front. You can have an h on the inside moving it to the right or the left, and you can have a k on the outside shifting it up or down. So the stretch or compression factor, all you have to do is look at the equation, and it's whatever the absolute value of a is. So if there's a number in front of the absolute value, that is our compression factor, okay? The vertex is going to be located at HK, and be really careful because H, remember, is the opposite of, it's being shifted in the opposite direction. So if I have absolute value of x minus 5, plus 4, if that's my function, then my vertex isn't -5. My vertex would be 5, 4. We take the opposite of what's on the inside to get this value right here. And then our axis of symmetry, instead of having to graph it and look at the line, all we have to do is look at this value right here. X is equal to h. And again, remember that we're going to take the opposite of what you see on the inside. So in this example right here, my axis of symmetry, x is going to be equal to 5. That's my axis of symmetry. So we can use this general form to find characteristics of the graph without graphing it, right? So, and this is something that you will be expected to do on the test and on the ACT. They like to ask these questions on the part of the ACT that you don't get to use a calculator on. So it says, without graphing, identify the vertex, axis of symmetry, and transformations from the parent function. So let's start with the vertex. All right, my vertex, it says, is HK. So here's my H. And notice that K is supposed to be right here, but there is no K. So K is actually going to be 0. So my vertex is going to be -6, 0, because I take the opposite of this, and there is no K, so it's 0. Okay. Now my axis of symmetry, I get x equals whatever the opposite of this is. So x equals -6. There's my axis of symmetry. And then it wants us to identify the transformations. So this graph right here is going to be shifted. This +6 means it's going to be shifted to the left 6 places. And it's going to be the 3 in front means it's going to be stretched vertically by 3. Okay, let's try that again over here. Absolute value of x -2, and then I'm going to -6. So my vertex uses h and k. So my vertex is going to be +2, because this shifts me to the right 2, and this shifts me down 6. So my vertex is shifted to 2, -6. My axis of symmetry, x equals the opposite of this number right here, so +2. And if I describe what's happening to my graph, this -2 means that it's going to be shifted to the right 2 places. And this -6 means that it's going to be shifted down 6 places. The minus means it goes down. There's nothing in front, so there's nothing stretching it or flipping it or anything else. It's just shifting to the right and down. Okay, so pause the video, give number 7 on the homework a try. See if you can figure out how to do that one on your own. Okay, last little bit, which kind of brings us to what we talked about at the very beginning of the lesson. Like all other functions, absolute value functions have a domain and a range. And we use interval notation to represent both of those. Okay, so just a reminder that a function's domain is all the possible values of x that can be put into the function. Or if you just look at the picture, what values of x does the graph cross? So for example, this graph right here, we're looking at the left and the right. And this arrow is going to the right forever, and this one is going to the left forever. So my domain on this example goes from -infinity up to infinity. And because they're infinities, we use parentheses. All right, so my domain is -infinity to infinity. On this one, it's going to be the same thing. It goes to the right forever and it goes to the left forever. So my domain is -infinity to infinity. Or in other words, I can plug in any x I want. That's not always going to be true, but with absolute value functions like these ones, it is true. And then a function's range is all the possible values of y that can come out of the function. Or if you're looking at the graph, what values of y does it cross? Or in other words, the up and down. So when I look at this picture right here, my graph goes up forever. That's what these arrows mean. It's going to keep going up and up and up to infinity. But going down, my graph stops right here going down. And it looks like that's at about +1, maybe 1.5. So I'm going to call that 1.5. And that's right where my graph hits. So I'm going to put a bracket there because it includes 1.5. And I'm going to put a parenthesis on the next to the infinity. So my range is 1.5 all the way up to infinity because it goes up forever. Okay. In this example, my range, again, it goes up forever, and it looks like I'm at about 1.5 again. So my range would be from 1.5 up to positive infinity. It's going to go up forever. Okay. Now, if this one had been down, let's say that this graph had been going the other direction. Okay. If this one had been pointed down, then it wouldn't go up forever. It would be going down forever. So I would actually have negative infinity at the bottom, and it would go up to 1.5. So that would be my top number, and I'd use a bracket there. Okay, I want you to give number 8 and 9 a try. So remember, homework 11, try numbers 8 and 9. When you are finished, you've got the rest of the homework to do on your own. Hopefully those problems gave you some practice as you're going through the lesson. And then the rest of the problems look a lot like what we just did. They're just more examples for you to try on your own. So give 8 and 9 a try. If you have any questions, come in and see me. Happy to help.